So we're on to page 16 in the booklets, and up to now, what we've done in this topic hopefully hasn't been too earth-shatteringly different from what you experienced at GCSE. So we looked at mass numbers, atomic numbers, working out different relative masses from the periodic table. I know the mass spectrometer was new, but it was just ways of working out the actual masses of different atoms. What we've got to in page 16 is called electron configuration. This is a bit new. And what we're doing here is updating your idea of how you think electrons fit in the atom. So the model you looked at GCSE with electrons and shells, that's certainly not wrong. We didn't teach any lies or anything. It's just not got the full detail we need at A level to explain how the electrons sit. So what we're going to do in this section is update your knowledge of how the atom works, specifically how the electrons in the atoms work. So to do that, what we're going to do, we're going to do a wee compare and contrast of what you learned at GCSE with what you need to understand now about the atom. So here's an example of an atom you've drawn at GCSE level. So an electron configuration with wee X's showing the electrons. So a couple of features just to go over again. You've your nucleus in the middle, which is called protons and neutrons, overall positive charge. You'll be glad to hear we're not changing it at all. It's exactly the same as you learned GCSE. The electrons, we said they're in orbits, or probably more likely we said they're in what we call shells. The first shell holds up to 2 electrons, it's filled up first. Then you get to the second shell, which holds up to 8, and then the third shell you learned holds up to 8, and the fourth shell we didn't get very far, you only put up to 2 in it, but it holds quite a lot. In terms of the rules we use for filling up shells, we learned that you got your clock face rule, where the electrons like to be by themselves first, but then they go up into 4 pairs when you fill up a shell before you go to the next one. And that's kind of the picture we had at GCSE. So what are we going to change, or what are we going to improve when we get to A level? The main change is this. When you had shells at GCSE, we're going to give them a different name now. We're going to call them principal energy levels. Sounds a bit more sciencey. And it describes kind of the energy levels you'll put electrons into. So you start at the first energy level, and you go to the second one and the third one. In terms of what electrons fit into each energy level, it's pretty much the same as what you looked at previously. So first energy level, second principal energy level, third, and we'll go up to fourth. So the first principal energy level, like the first shell at GCSE, it holds up to 2 electrons. The second principal energy level, a bit like the second shell at GCSE, it can hold up to 8 electrons. Now, wee difference here. The third shell at GCSE held up to 8 electrons. In reality, it actually can hold up to 18 electrons. And we'll talk about a wee bit why they've got that wee inconsistency in a second. And the fourth one, which we never really got to GCSE, and to be fair, we never really go into that much at A level either, it actually holds up to 32 electrons. So some similarities and differences. Same idea in that we've got individual layers that electrons can go into, and you have to fill up the first one before you go to the second one, before you go to the third one, etc. We've slightly changed how many electrons are in each layer. Now the first 2 are the same, 2 and then 8. We've got slightly more in the third level and slightly more in the fourth level. But again, just bear in mind, it's just layers that you put electrons into. Okay, so that's one difference. The next difference is that these principal energy levels are split up into what we call sublevels or subshells. That kind of term is kind of used interchangeably. So what we're saying there is, within each of these energy levels, instead of thinking about them as one individual kind of consistent layer or shell, they're actually split up into sublevels or slightly smaller levels within each of these. That sounds a bit bonkers, but let's see where we get with it. So let's just break it up. So the first energy level, second principal energy level, third principal energy level, and fourth principal energy level. Let's see what sublevels we've got in each one. So we said they've got sublevels, but they haven't all got the same number of sublevels. The kind of real weight or power we see is, as you get to higher principal energy levels, you start getting more sublevels. So the first principal energy level actually only has 1 sublevel or subshell. And we call that sublevel, well, if I come back to the names after, we'll just do layers first. The second principal energy level has got 2 different sublevels to it, or subshells. The third one, you've probably seen the pattern now, it's got 3 sublevels. And the fourth one's got 4 sublevels. So you maybe are struggling already, but let's not get too bogged down. All we've changed so far is we've changed the name of our shells to make them now principal energy levels with different numbers of electrons filling in each one. The new thing we've introduced is that it's not like a shell we've got like just like one individual kind of uniform layer. We've actually got a wee bit more complicated structure. We've got sublevels within each of these layers. So we call them sublevels or subshells, and you get more sublevels as you get to higher principal energy levels. So the first one's just one layer, second one has got 2 sublevels, third is 3, fourth is 4. Now you might be thinking, well, how do we keep track of all these different sublevels? We give them individual names, and the names are a wee bit funny. The first sublevel, or like the lowest energy sublevel of each group, is given the letter S. So the first sublevel will be 1S for first principal energy level, the S sublevel. The first sublevel of the second energy level will be 2S. The first one of the third will be 3S, and so on 4S. So the lowest sublevel of any energy level is always given the letter S. For the first sublevel, that's where we stop, because like we've no more room. We've just got one sublevel filled up. But in the second one, we've got another sublevel to put in because we only got one there. The second sublevel of any energy level is called P. So 2P, then the second one for 3 will be 3P, and then 4P for the next one. So that's now our second energy level filled. Third one, it needs one more, it needs to get up to 3. The next random letter is D, so we go to the 3D level, and 4 will have that as well. And then 4 needs one more, it's going to have F. Now, you're probably thinking this is some bizarre language. The reason we got letters, it's kind of like a historical reason. It's where the way they discovered these different sublevels, they gave them original names, which we've sort of shortened down to S, P, and D. It's kind of arbitrary, doesn't really matter. Just that's what we call the different levels. So following through again, what we've got, again, don't want you to get lost here. These are what we called shells at GCSE. We're now calling them principal energy levels. They're split up into individual sublevels within each layer. And we give different names to the different sublevels within each layer. So the first one of any group is called S, then P, then D, and then F if we get to there. Now we're going to combine two things together. We've already looked at how many electrons should fit into these energy levels. Let's see if we can actually put them in the correct place. So we said the first sublevel holds up to 2 electrons. The first principal energy level holds up to 2 electrons. The second principal energy level holds up to 8 electrons. The third one, 18 electrons. The fourth one, 32 electrons. So how do they actually fit in? Because we've got to put them into the different sublevels, but it might not be kind of uniform how they fit in. So whenever you've got an S sublevel, no matter where it is, it can only hold up to 2 electrons. So that's the same for 1S, because it actually fills up the 1S energy level completely. The 2S can hold up to 2 electrons. 3S sublevels can hold up to 2 electrons, and the 4S sublevel holds up to 2 electrons. So that's consistent throughout. S means holding 2 electrons in that sublevel. If you think about the second principal energy level, we've got 2 electrons can fit into 2S, but we have to get up to a total of 8 electrons. We've only got one sublevel left to fit that into, so that therefore must mean that any P sublevel can hold up to 6 electrons, because 2 plus 6 equals 8. That's all our sublevels we got, and we got to fit 8 electrons in there. That'll be consistent as well for the other ones. So the 3P is a P sublevel, so holds 6 electrons. 4P holds 6 electrons too. If we turn to the third one now, so we've got 8 electrons so far in the third principal energy level. We have to get up to 18. So that therefore must mean that the D sublevel must hold 10 electrons. And that hopefully should be the same for the 4D. Now we get to the 4F, which we don't really talk about in AS, but we'll just complete it for completion's sake. Up to 32 electrons in the fourth energy level, we've got 18 so far. Therefore, we need 14 electrons left over to get the 4F filled up. So all we've added in at this point is, if we're saying electrons have to fit into principal energy levels and into sublevels, we need to know how many electrons fit into each sublevel. What's important to realise is that the sublevels are consistent, so even when you get up to higher energy levels, an S sublevel will always only hold 2 electrons, a P will only hold up to 6 electrons, a D will only hold up to 10 electrons. It's just a matter of which sublevels are in each energy level. The final thing to put together, whilst I know this is hard, is to try and kind of visualise a wee bit like, you might be thinking, okay, I can follow kind of sublevels, electrons are going into sublevels, but what does it kind of look like? Like how does it actually sit in the atom? To answer that question, we need to think about the idea of an orbital. So orbital as a word looks a little bit like orbit, like we had at GCSE. And what an orbital describes is how the electrons are sat around the nucleus, or in like the electron shells or energy levels. An orbital is a region of 3D space that holds up to 2 electrons with opposite spins. Now, I'm going to leave out some of the definition for now, just give me the full one for now. Opposite spins, I'm going to leave that for later, it doesn't really matter. But the important thing is that it's a region of 3D space. It's an actual region within the atom where you'll find those electrons in that orbital. The important thing is it only holds up to 2 electrons. So all these sublevels are made up of orbitals, but for some reason an orbital itself can only hold up to 2 electrons. That must mean we have quite a lot of orbitals to fill up. I'll explain what that means. For example, the first sublevel we get to is the 1s sublevel. It holds up to 2 electrons, so that must mean that represents just 1 orbital. And that'll be the same for the 2s, it holds up to 2 electrons, it must be just 1 orbital. However, when we get to 2p, it holds up to 6 electrons. It's made up of orbitals, but orbitals only hold up to 2 electrons. Therefore, there must be 3 2p orbitals making up that sublevel. Because 3 times 2 electrons means 6 electrons. Back to 3s, that's just one, sorry, I should probably give them a name. It's a 1s orbital, 2s orbital. That'll be a 3s orbital. Holds up to 2 electrons. Again, with our 3p, we need 3 3p orbitals to get us holding up to 6 electrons. And then d, we've got 10 electrons, that means we must have 5 3d orbitals. The 4 we'll just do quickly. 4s holds up to 2 electrons, it must just be 1 4s orbital. 3p holds up to 6 electrons, it must be 3 4p orbitals. 3d holds up to 10 electrons, it must be 5 4d orbitals. And then the 4f, 14 electrons, and must be 7 4f orbitals. And that's the kind of the extent of the detail we need to know. I know it does look quite complicated, but we'll put it all together one last time. So, at GCSE, we had shells. The first shell, second shell, third shell, and fourth shell. We learned how many electrons those shells hold and how they sit, and we arranged them. Fair enough. What we said now is that these are called principal energy levels. The reason we call them principal energy levels is because they're not nice, neat shells. They're made up of subshells or sublevels. The first sublevel holds up to the first principal energy level has 1 sublevel, second has 2, third is 3, fourth is 4. Sublevels hold a specific number of electrons. So all the 1 sublevels hold up to 2. 2 sublevels in the second one holds up to 8. 3 sublevels gets 18, and 4 sublevels gets 32. Those sublevels have different names. So the first sublevel of any principal energy level has S as its letter. Second one is P, third one is D, fourth one is F. And those sublevels hold specific numbers of electrons. So an S sublevel always holds 2 electrons, a P sublevel holds 6 electrons, a D sublevel holds 10 electrons, and F sublevel holds 14 electrons. The final complication is in terms of how it actually works in 3D space. Those sublevels are made up of orbitals. Orbitals are little pockets of space, like different shapes, and within those shapes you'll have electrons whizzing around. The rule is, though, that orbitals can only hold up to 2 electrons. So you need quite a few orbitals to get the whole picture kind of fitted in. A 1s sublevel holds 2 electrons, that just must be 1s orbital is what we call it. Same with 2s is a 2s orbital. 2p, a little bit different. We need 6 electrons in that 2p sublevel, therefore we must need 3 2p orbitals to get that fit in. Going through the third one, we get to 3d, need 10 electrons, must therefore need 5 3d orbitals. And then the fourth one, we get spd, and F needs 14 electrons, therefore it must need 7 4f orbitals. Now, if you understand that kind of maybe 70-80%, you're probably fine for now. As we work through the rest of the booklet, it'll become a lot more familiar with the terminology we're using here. To stick with it for now, I promise you it will make sense in time.